All right, so let's see if we can figure out parametric curves.
I just heard that term yesterday.
Yeah, my claim is that these are actually really easy. I'm going to start throwing all of these away. Okay, so the idea of a parametric curve is you have two functions. You have, say, x of t is t, and y of t is 2t. What?
Because don't you have to solve t for t or x?
Okay, so think here, right? This is x is a function of t, and that function is just given by t. And then here's a function of t that gives you y, and that's 2t. So this is a lot like, right? I think what I'm thinking here is I'm thinking of a point, right? And the first coordinate is what? T. And the second coordinate is 2t. And so then I might, I don't know, here, let me give you a range for t. Let's say 1 is smaller than t is smaller than 3.
Whoa.
Okay? And then we should be able to graph this. So where does this thing start?
Starts. Starts. Negative infinity. I don't know. No, it starts at
Okay, so where do the t's start?
1.
T's start at 1. So when t is 1, where's x?
X would be at 1.
1, and y is at 2. So if I go to the point 1 comma 2, right? What I'm really thinking there is t equals 1. You guys with me on that? Okay, then what happens? Okay, yeah, we could plot some more points. So when t is 2, what's x?
2.
X is 2. And what's y?
Square root of 16.
Perfect.
Good one.
So this one's 2 comma 4, right? And for 2 comma 4, we're thinking t is 2, right? And this is the thing that can be different about parametric curves. How did you get from 1, 2 to 2, 4? Yeah, there's two different functions. One's giving you the x values, right? The x values. The other one's giving you the y values. Keep in mind, there's a lot of ways to get from 1, 2 to 2, 4. This one in particular has, if you fiddle this a little bit, right? If you change the x a little bit, what does the y change by? Double that little bit, right? So a little bit of run gets you twice as much rise. That's a line, right?
Right.
You guys all see that? So I have this line. Where does this thing stop? Yeah, that stops at 3, 6, which is really me thinking t is 3, right? You guys see that?
Do they have to be separate, or can we compound them like this?
Okay, so you can sometimes, not always, but sometimes, you can use the trick that Connie was sort of pushing on, which is that you can solve for t. You guys see that? So this is really saying x and t are the same thing. So over here, you could plug in y, right, in terms of x. So what's y in terms of x? Yeah, y is 2t, right? But t and x are the same thing. So really y is 2x. Big surprise, I'm getting a piece of the line y equals 2x. You guys all good? This is like the most boring this gets. Cool? Better example? Okay, better example.
Let's do a cubic.
Let's not.
Aw.
You really want to do a cubic next? We can do a cubic, sure. Okay, so let's do this one. Y is t cubed, or sorry, x is t cubed and y is t, and we'll go from minus infinity is smaller than t is smaller than positive infinity. And maybe we'll cut out the equal signs there so we don't have to deal with whatever that would mean. Cool? Okay, so I would like to draw a picture.
I'll go with T.
So we could plot some points. What happens when t is 0?
0, 0.
Okay. So I'm getting this dot 0, 0 when t is 0.
Mhm.
Okay, then when t is 1,
1, 1, 1.
you have 1, 1. How about when t is -1?
Oh,
-1, -1. Is this a line?
no.
No, we're still following the cubic expectation.
Oh yeah, that looks like a cubic, kind of. How about when t is 2? X is 8, right? And t is, or sorry, and y is 2.
One. Yeah,
Right? I get 2 comma 8, which is really t is 2. How about when t is -2?
When T is -2, X is -8.
-8, and y is -2, right?
What are you trying to pull here?
Good. What am I trying to pull here? What's the relationship between x and y? Y is t, right?
Yeah,
So
X is Y cubed.
x is y cubed, right?
F of X
You guys see
equals
that? So that's
cube root X.
That's doing a dirty trick, right? That's the x-axis and this is the y-axis. If you twist your head this way and put it through the wall, right, then you can see the usual x cubed. You guys see that? I just switched the response to the input variables. So what else is this a graph of? Like, if I draw this, this is,
That's an inverse cubic, right?
yeah, this is the inverse of the cubic function. This is the cube root function. Yeah, exactly. So if you solve this equation, right, you'd cube root both sides. So you get y is the cube root of x. And of course, yeah, here's that picture. And then what's the difference, oops, that's not where that goes. What's the difference between this curve, right, and this idea?
None?
So the set of points that make up this curve and the set of points that make up the graph for that are the same. This one has a method by which it traverses. You see that? Like this has an itinerary, and the other one is just some points. You guys see that? No.
So one is more true than the other, per se?
No, no. Just this one has a little more information to it. This kind of tells you, like, this function, right, just tells you where x's go and what they give you for y's, right? This thing is very similar in feel, but it has an itinerary. It tells me what kind of time this thing's happening at. You guys see that? You want a better example of that? Okay, let me give you a better example. So, one, I'm going to give you an example that's not actually the graph of a function now. So, let's say x is cosine t, y is sine t, for 0 is less than t is less than 2 pi. Cool.
Alright, so at 0, X is 1 and Y is 0. That's a point on the line.
Okay, so when t is 0, we're talking about out here. Okay, and then what's t playing the role up here? No, close.
The angle.
You had me until you said us. No.
Radians?
Yeah, t is playing the role of the angle in radians. You guys see that?
Radians?
So if I change the angle, right, what happens? Well, what's the radius here? 1, right?
Yay.
You guys see that? Really, this is me thinking about the usual unit circle, right? So here's a dot. This is an angle t. And I'm saying that x is cosine t, which is identically, right, the adjacent side. I'm doing this one. And the y is sine, so that's the other side. So I get what out of this? Yeah, I get a drawing of a circle.
Good lord.
And the thing about, there's a little more information here, is that this circle goes this way and is traversed once. You guys see that?
Oh, because we can't go past 2 pi.
Yeah, because our t's, right, live between 0 and 2 pi. That's cool. Am I convinced?
Yeah.
Okay. What's the difference between, let me call this curve 1, and we'll call this curve 2, which is x is sine t and y is cosine t, and we'll go from 0 smaller than t to 2 pi.
So we have 0.
That's the circle going the other way?
I don't know. We have to figure it out.
I feel like it's going to start in the middle.
Okay, so when t is 0, what's sine of 0?
Sine 0 to 1.
So when t is 0, x is 0, and y is 1.
Yeah. Starts up there at pi.
So curve 1 starts up here, and then how do I figure out which way it's going?
Go
It's
to
positive.
pi over 2.
Yeah, so if I increase t, right? Sine looks like this. Cosine looks like that. This is the x's, so the x's are going up, and the y's are going down. So that's movement this way. You guys see that? So they're the same curve, right?
In a different direction.
But a different direction and
Starting point.
different starting point. Okay.
What if we did some tanny stuff?
Okay, hang on.
Sorry.
So the blue is curve 1, the black is curve 2, and then here's yet another one. If x is sine of 2t and y is cosine of 2t, and t's live between 0 and pi,
It'd be a double the size circle.
hang on, I call that curve 3. Ah, that's a good idea though. Would it be double the size?
Half the size?
I haven't changed the radius, right? Normally in polar, the radius lives right here, right? That have x is r, whatever, and y is r, whatever.
Sounds like half a flower now.
Okay, you still have a circle. All I did was change the, yeah, exactly. I changed the speed. So curve 3 and curve 2 are the same curve, but curve 3 is traversed twice as fast. Yeah, so this is an adjustment of angular momentum, or angular velocity, really. You guys cool with that? So there's lots of ways to skin these particular cats, right? What? That makes sense. Don't give me that. But the important thing is that you know that it's not just a graph of points, right? It's a set of points, it's got a direction and a speed, and sometimes it does weird stuff like double back on itself for a little bit.
Wait a second.
What?
Wait.
What?
Wait.
Vector?
This thing? Yeah, these are vector functions.
Golly.
So if you want to think about this as in vector land, you think to yourself, right, this is v of t, which is given by cosine t comma sine t, And the domain, right, is 0 is smaller than t is smaller than 2 pi. You guys see that? These are really vector valued functions.
Well, that makes
in
sense,
some
that
sense.
gives more information.
What's that?
That's why we give more information.
Okay.
It's not, it's more than, the point is a vector.
Yeah, it's more than a point, it's a vector, and right, it's got some kind of input variable that means something. You guys cool with that? What? No, I wrote it as vectors. Don't give me this. Don't give me this vectors with parentheses bullshit.
That's inner product representation.
Yeah, because it's hard to tell inner products from vectors.
Vectors are in inner product. And that's what we said, inner product is vectors.
Yeah, so you get to pick one. Do you guys recognize this? I think in our trig book they use these for vectors. Right? This is a vector B. Something like this. Yeah, the pointy things I tend to use to mean vectors, but they also mean something else. But this also means a point, right? So there's some confusion there. It's okay that there's confusion there. You get to pick where the confusion is.
Anything that is always have, like.
Because there's a lot of things and we ran out of names.
Yeah, we have a lot of things and we ran out of symbols, and these were invented relatively recently, so they haven't settled down yet.
Make sure